Warning, the video you're about to watch contains mathematics at the level of college algebra and trigonometry. All material has an assumed prerequisite of both Algebra 1, which is elementary algebra, and Algebra 2, which is intermediate algebra. While some prerequisite topics are reviewed briefly, a more thorough review of these entrance topics can be found by searching the web.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcome.
Hello, my name is Roy Simpson, Professor of Mathematics at Cosumnes River College in Sacramento, California. This lecture is for college algebra students who are first encountering power functions, and we're going to spend a little bit on the end behavior of power functions here and the end behaviors of polynomials. And that's really the focus of this lecture series or this next set of videos. So identifying the end behavior of power functions, I guess the first thing we need to talk about is really what is a power function. And if you were never introduced to that in your intermediate algebra or algebra 2 course, that's pretty understandable because not a lot of people really call them that anymore. But a power function is just a function of the form k times x to the p, where x and p are real numbers. K is called the coefficient. So that's all written out here, right? So some examples of power functions would be something like f of x is equal to pi times x to the third. That's a power function, because again, the coefficient and the power are both real numbers. Another power function, g of x is equal to 1/2 x to the negative, let's say negative 3/7. That's also a power function. So again, because both its coefficient and exponent are real numbers. And finally, another power function, x to the pi power. There you go. Those are, the coefficient is 1 and the exponent is a real number pi. So there you go. Those are power functions. So I'd like to embed a little bit of review in what we're doing. So think about all the base functions that we've dealt with and that you have memorized as far as graphs go up to this point in algebra, and consider which of those are actually power functions. We'll go through in the order that you likely learned them. For example, the first one is y equals k. That is the constant function. And that's definitely a power function, mainly because, maybe I should put the check mark over here, because it can be written as k times x to the 0th. And so x to the 0 exponent is a real number, k is a real number, and there you have that. The next one you learned was y equals x. That's a base graph you've learned. That's just a graph of the linear function with slope 1 and y-intercept 0. And again, that is a power function because the coefficient is a real number and the exponent is a real number. So yep, that's a power function as well. And if you graduate through mathematics here, y equals x squared was the next power function, or I'm sorry, the next base graph that you were introduced to. You know its graph is that of a parabola. And that definitely is a power function because its coefficient is 1, its power is 2, and both of those are real numbers. So you probably get in the idea that most of our base graphs, our base functions, are actually power functions. Even x cubed, I'm not going to write it out slowly. Instead, I'll just say yes, because it's 1 and a 3 as far as the coefficient and the power are concerned, respectively. Let's see. The next set of base graphs, the square root of x. Well, that can be written as x to the 1/2, as we know. So therefore, that's definitely a power function. Another one that you should know the base graph of, y equals the cubed root of x, which is x to the 1/3. And yes, that's definitely a power function as well. A couple other ones that you have learned. Y equals, well, when I teach this, this is kind of the order I go in. So y equals the absolute value of x. Now that is not a power function. And the reason why it's not is because it's not just x to a power. The absolute value is a completely different beast of a function. And so it cannot be written as just x to a power. It is actually the absolute value of x. There's nothing else you can do with that. You can write it as a piecewise defined function, but other than that, you're pretty much stuck there. And let's see, the others, I think we have two more. Y equals 1 over x, that's a base graph, you know, and that is just x to the negative first. Negative 1 is a real number, so therefore that definitely is a power function. And likewise, the square reciprocal function, which is x to the negative 2, is also a power function. So quite a few of our base functions are power functions. And that is kind of nice. So we deal with power functions very often in mathematics. In fact, that's kind of the end game in mathematics, is to convert as many functions that you're handed into power functions, specifically polynomials. So let's go ahead and see what else is on our agenda. Now we're going to have to talk about the end behavior of the graph of a function here, because that ends up dominating quite a few large topics in both pre-calculus, which is after your college algebra course, and calculus. So you do have to understand what end behavior is. And by definition, the end behavior of the graph of a function is the tendency of that function, the tendency of the function values for that function as x goes to infinity and as x goes to negative infinity. By the way, that arrow symbol, that means as x goes to or tends to. So I'll go ahead and write that down. So whenever you see that arrow in mathematics from this point forward, you should just imagine that it's saying x is tending to negative infinity, in this case up here, or x is going to negative infinity. Tending to is kind of a more rigorous way of saying it, but it is true that it's just going to or heading towards or whatever that value. That is a calculus notation, and it's good that you get used to it now. So the end behavior. I could give you graphs of a function. For example, let me give you the graph of a function you already know. This is the graph of the exponential function e to the x. So let me graph this out. It looks like this. All right, and if it's e to the x, I'll just call this f of x equals e raised to the x power. It goes through 0, 1 and 1, e. So it goes through those 2 points. And you should know from exponential functions from algebra 2 that as x goes to the negative direction here, our function, our exponential function, gets closer and closer to the x-axis, but it will never actually intersect the x-axis. And the way you would write that in terms of end behavior is you would write it this way. As x tends to negative infinity, f of x tends to 0. It's getting really close to 0 as x moves on. I'm going to zoom in here. As you move to the left, as x is going to negative infinity, the y values, which are the function values, that's what we'd call those, they're tending to a height of 0. So that's how you would write this using calculus notation. And the end behavior is that as x goes to negative infinity, the function values tend to 0. Now this function actually has two different end behaviors, because as x goes to positive infinity, the y values keep rising and rising. And so we would just say it this way. As x tends to positive infinity, and by the way, I don't put a positive in front of the infinity sign. It's assumed. It's just like you don't say I have positive $3 in my pocket. It's assumed if you say I have $3 that it's positive. So as x goes to infinity, your function values will climb also towards infinity. Little aside here, infinity is a concept. It's not actually a number. And so you can't say f will equal infinity. That's not true. It will approach infinity. Just like x cannot equal infinity. That's a concept. It will approach infinity. So there you have it. That's kind of the discussion about what end behavior is in general. Now we're going to go ahead and dive a little deeper just into power functions. So let's use Desmos to graph power functions of the form y equals x to the 2k, where k is a natural number. Now you really do need to get used to this 2k notation. think about natural numbers. Natural numbers 1, 2, 3, 4, and stuff like that. And now multiply any natural number you want by the number 2. And all of a sudden it becomes even. So this is a fancy way of writing an even number. And it's actually the best way to write an even number, to be very honest with you. So I'm really looking at power functions of the form x to a power where the power is even. That's really what we're considering. And the question is, if we graph a few of those, what's the end behavior of these functions? And then when we're done with that, we'll look at the end behavior for negative x to the even power. So let's go ahead and do that. So the first thing I want to draw your attention to is how I build functions in Desmos. I type in there f of x is equal to x to the 2k. I'm literally just typing it in the way that I told you I want to type this in, x to the 2k. And then after I do that, in fact, maybe I'll just do this. It says, do you want to add a slider for k? The answer to that is definitely. I want my slider to start at power of 2 and maybe just go to a power of 10. And I'm going to step by 2s. Okay. So this is allowing me, maybe I'll go to 20. But I want to step by 2, so I only get, actually, I'll step by 1s. Now that I think about it. Oops. K equals 2. I'm starting at 2. No, I can start at 1. What am I talking about? All right, we'll step by 1s, actually. Because it's whatever K is, it's going to double it up and make it even. So we're okay. All right, let's go ahead and see what happens. Okay, so there's for K equals 1. Let me zoom in here. It's a nice, you know that, right? If k is 1, you have x to the 2 times 1 or x squared. But if you move this up, here is x to the 4th, because it's twice 2. Here's x to the 6th. Here's x to the 8th, and so on and so forth. You can see actually what happens. A lot of people will say the curve gets flatter, like it's a tire. And then as the power goes up, it becomes more of a flat tire. But still, as far as the end behavior is concerned, it looks as though as x goes to negative infinity, the y values keep rising. As x goes to positive infinity, the y values keep rising. And actually that'll be the case in all of these functions. Although you see, some people will say it looks like it gets narrower. And some people will even say, I don't think that it continues to go to the left after maybe this x value right here, but it does go to the left. I could plug in x equals negative 20 into that function. It just will be a massively large number off the screen. So there's no point in me trying. But the reality is the end behavior still goes up and up. In other words, as x goes to negative infinity, the y values go to positive infinity. And as x goes to positive infinity, the y values go to, again, positive infinity. And this is summarized by just saying, listen, for that y equals x to the 2k, x to an even power, as x goes to either plus or minus infinity, in other words, as we look far to the left or far to the right as far as x values are concerned, the y values or function values climb to infinity in both directions. That's the way you would note that. Now let's go ahead and look at the end behavior of negative x to the 2k. Now here's my function again. All I'm going to do is just throw a negative in front of that. Boop. You can see the end behavior here as x goes to negative infinity. The y values are dropping to negative infinity. And same thing, as x goes to positive infinity, the y values will fall forever. And if I increase the power, remember these are all even powers, same thing actually. The behavior does not change. It just falls forever on either side. Therefore, as for y equals negative x to the 2k, or negative x to the even power, as x goes to the left or right along the x-axis as far out as we want, the function values will dive down to negative infinity. So this is a general behavior of even degreed or even powered power functions. What about odd powered power functions? This is the same style of question. Again, hopping over to Desmos, we'll just take a look at x to the 2k plus 1. Again, 2k plus 1, what does that mean? That's very popular in mathematics to write numbers as 2k or 2k plus 1. What we just had said last problem was 2k, where k is a natural number, is going to be even. Well, if you add 1 to an even number, well, you should probably know you get an odd number. So this is just an odd number. So now we're looking at power functions with odd exponents. Here we are. I'm going to put a little +1 here. And when I put that except I put the +1 in the wrong spot. I want this in the exponent. Oh, okay. So a little lesson in Desmos. If you want to make an exponent have an addition or a subtraction, you have to start a parenthesis. I forgot about that. So +1. There we go. Coding 101. All right. So you can see here's an odd degreed power function. And I have a colleague who calls it the disco function because, well, it looks like somebody doing the disco dance, I guess. All right. But if we increase the power on that, so it's a third degree, well, here's the 5th, the 7th, the 9th, and so on and so forth. You could see that actually the pattern doesn't really change. To the left, as x goes to -infinity, the y values fall. And to the right, as x goes to +infinity, the y values rise. So that's a good pattern. It retains that pattern no matter how high I take that odd power. Although you could see low odd powers have this nice smooth curvature to them, but the higher the odd power gets, it gets flatter and flatter, like a flat tire. There's a reason for that, actually, but we will discuss that a little bit later. So this one was slightly different, right? As x went to -infinity, the y values or function values fell to -infinity. On the other hand, as x went to +infinity, the y values, again, function values, rose to probably +infinity. And now we can go ahead and look at the opposite of that. So we're going to look at y equals negative, but you already kind of know what's going to happen because you have exposure to transformations of functions. This is just going to be the same old function we just graphed, but rotated about the x-axis. So there's not a real big reason for me to showcase this on Desmos. I'm going to do so anyway. And you can see it starts high, goes low. It just rotated, literally just rotated about the x-axis. See? Here's it without the negative, and here it is with the negative. It just rotates about the x-axis. Otherwise, the behavior, whether it's a third power or a 21st power, actually that's a 41st power, the behavior remains the same. It starts high, goes low. So as x goes to -infinity here, the y values go to +infinity. As x goes to +infinity, the y values dive down to -infinity. And this is just me writing down what exactly I just said. So far, I think that this should be pretty okay for most students. You guys have probably seen this already, but let's go ahead and take an example. Let's go ahead and identify the end behavior of this function without graphing it. So it's odd exponent on there. It's a power function, has an odd exponent. I'm just going to point an arrow and say that's odd. And it has a negative coefficient. So negative coefficient, odd exponent. Well, I said I wasn't going to graph it, but I am going to do this. Normally, odd exponents start low, go high, but you rotate, that negative exponent makes you rotate this about the x-axis, and so you end up with this starting high, going low. And so now, don't just leave that graph as your answer, please. What you want to do is just state it in calculus style language. Say, as x goes to -infinity, f of x, is that what we're dealing with? Well, they didn't name it. I'm going to call it f of x, goes to +infinity, according to my chicken scratched graph there. And as x goes to +infinity, our function dives down to -infinity. Very fast question to answer, but it's really important that you get used to these ideas. It has to become second nature, that you're able to answer these questions very quickly. Now, as far as power functions, that's all we're dealing with in this video. So the next video will deal with polynomials.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes obstacles getting in our way, cause affects more than we can sometimes see. Things for what they are and work together until you feel at peace. Listen close, don't talk too much, that is missing cold. Sure, you may really hurt inside. It doesn't justify you to speak too loud and cry.